Okay, so good afternoon, Professor. It's a great honor for me to have this opportunity to talk with you about the future of information theory and wireless communications. Many scholars are focusing on the so-called finite blocklength information theory. Mm-hmm. And you are also a very established scholar in this area. So could you please give us a general overview of this area?
The Shannon theory, and more in general information theory, has been around for a while. It's a well-assessed and relatively mature area where a lot of results, a lot of important results have been proved. The strength of information theory is the ability of proving rigorous results. Yeah. And giving fundamental limits. It is true that the original approach of starting with Shannon is asymptotic in the communication length and the duration. There is no notion of delay, random activity, random access, users that may transmit or may not transmit, and is a very fundamental problem. We want to transfer some bits from point A to point B, and in a multi-user scenario, we have this maybe a complicated network, but it's about basically determining the rate region that is achievable. By achievable, I mean it is possible to transmit with arbitrarily small probability of error in the limit of large block length. More recently, people have revisited what happens at, let's say, non-asymptotic transmission length. Even at the time of Shannon himself and people who immediately followed his work, for example, Gallager, Caire, it was all about determining error exponents. In fact, problems for which the error probability would not decrease exponentially in the block length were considered to be not quite interesting. There is even a sort of joke that when Gallager discovered LDPC codes, which are now used everywhere, and he discovered them in '63. So imagine, it's like, but for some reason they couldn't prove, and in fact it is generally not true, that for this type of codes the probability of error goes to zero exponentially in the block length. And so in a certain sense it was considered not a very interesting coding technique. Of course, we know now that it's a very interesting coding technique. All the modern standards use it. So this is to say that this idea of trade-off between the probability of error and block length has been there from the very start, from the very early days. However, they looked at the problem in the so-called large deviation regime, which is asymptotically, exponentially small probability of error. And this makes sense when the block length is finite but still very large. More modernly, with the work of Verdun and Polyansky and Poor, and then all the people who followed, they looked at a different regime, at the regime of basically what is the best rate you can obtain at a given fixed probability of error that does not vanish, is fixed, and at a given length. And this is in a certain sense, a complementary way of looking at the problem, which is, of course, much more in line with the practice, because in practice we have finite block length and we try to do the best we can, so transmit at the highest possible rate within a requirement of probability of error that don't need to be exponentially small or vanish into zero. A system today, a system that at the physical layer achieves a block error rate of between 10 to the minus 2 and 10 to the minus 3, we know that is a working system because there are other mechanisms to take care of these residual block errors at the higher layers, for which a network that operates at the physical layer in this way, especially in the wireless case, is not needed to achieve probability of errors that are astronomically small, like 10 to the minus 15 or something. Of course, things would be different in different areas. For example, if we look at the optical communication, it's clear that when you transmit many terabits per second, probability, a bit error probability of 10 to the minus 3 means that you have like millions of wrong bits in a code word, which would be very, very problematic. So of course, we have to clarify and define our environment. Now, having said that, this finite length approach and this different angle in looking at the problem is definitely more in line with applications, modern applications. So, for example, low latency, and also has led to alternative formulations that include, for example, random user activity. For example, the famous unsourced random access, which is an information theoretic way to essentially describe what we already do in actual systems. So the random access in today's system, basically the accessing code in the so-called RACH slot, every device uses the same code book. There is for example, a library of preambles, your favorite preambles out of 2 sequences or whatever, and every device uses one of those. The information that is specific of the device, like for example, the ID, the MAC address, or who knows. Well, this comes later. This comes in the payload, because in order to access the system for the first time in a completely random way, somehow the system must know what is being transmitted, and you have potentially an arbitrarily large number of users that are idle, and only a few transmit. So in this context, basically now information theory, and in particular finite length information theory, is also able to handle random access and sporadic access situations which are more representative, for example, of machine-type communications and these kind of things, right? So I would say this modern theory is catching up pretty quickly with real-world applications. And the results that have been produced more recently are actually very relevant in the sense that not only there are elegant results, like theoretical results, but that these can also be approached fairly closely with actual coding techniques, especially in the random access area. So, other than that, I would say that the finite length information theory is mostly has focused, I would say, on a single classical point-to-point channel and the multi-access case with the flavor of unsourced random access. There are, of course, many more network topologies for which even the classical information theory is not so well assessed. There are problems that are still open today, even in the classical sense, and even more in these new, say, finite length scenarios. The problems become even more challenging.
The major motivation for the finite block length information theory is we need to try to bridge the gap between theory and the practice.
So information theory has always this operational side, which is, let's call it coding theory, but also signal processing, statistical signal processing, communication theory. So all the techniques that go in the direction of actually achieving the limits predicted by information theory. Information theory typically is non-constructive. It's very rare that some proofs are actually constructive, that you come up with a fundamental limit by constructing explicitly a code. Even when people say code construction, typically are random ensembles and random coding results, which means averaging over an ensemble of codes. And this was actually one of the brilliant ideas of Shannon, to somehow bypass the difficulty of constructing optimal codes by basically randomizing and analyzing the ensemble average error probability. And of course, in order to achieve these limits, one has to, once you have proved the existence of good codes that achieve certain performance, one has to construct them. So construct them, of course, coding theory is one thing, but today I would say coding theory per se is also quite mature. Every now and then there is a new family of codes, but say the last big breakthroughs were the turbo codes in the 90s, the LDPC, rediscovered of the LDPCs in the 20s, and now the polar codes is the last. And maybe, who knows, maybe there are a few more things that have come out, like these sparse regression codes and maybe probabilistic shaping as an alternative to map binary codes over high order modulations for high spectral efficiency. But I would say that even the finite length information theory still rely on ensembles and random coding approaches. So eventually one has to construct codes, but knowing, you know, the block length and the size, the rate, and the error probability that can be achieved, then the challenge is to construct coding schemes that actually get close to it. And in some cases, the performances are not so far apart. So there are cases in which the final length information theory predicts certain performances, and then you see certain families of codes, like a good, well-designed DPC codes or polar codes that actually go fairly close.
Thomas Caire, a very famous scholar in the information theory, he once said, communications are constrained by computing, and computing is also constrained by communications. It implies that there is a fundamental trade-off between communications and computing. The current information theory is essentially communications-oriented or communications-centered. So how to develop the computing-oriented information theory?
So actually, there is a quite developed area in between, I would say, information theory, coding, and computing, especially considering network coding. So, of course, when we think about a communication network, there is a physical layer, and the physical layer, if we have a wireless network or we have an optical network, is whatever it is, right? But the functionalities of computing typically live at, let's say, the application layer. So application layer is here, the physical layer is there, there are many protocols in between. Now, is it optimal to have these layered protocol architectures? Probably not. Is it practical and attractive? Yes, because the people who develop the physical layer, so the companies that develop the physical layer they want to have a product that can sell to a large market, and the people who develop applications or run large language models, so that the AI, they don't care really if their bits go through a fiber optic or through a Wi-Fi network or who knows, right? So it makes sense. Having said that, in a data center or in a network of data centers, more in general, there is a topology. Right? There are computing nodes that communicate with each other. And for example, there are applications like federated learning, where it is essential to be able to exchange data and update gradients, local gradients, subject to certain privacy requirements, subject to certain robustness requirement. For example, some nodes may not respond, so they're like so-called dropouts. Some nodes may respond too late, so the so-called stragglers. So as a matter of fact, there is a line of work that has considered this topologies rather, I would say, a high level, so more like at a logical level, which are more proper of the area called network coding, where you have a network topology and basically the links are logical links, say capacitated, meaning that they can transmit bits at a, say, given rate. But we are not concerned with errors at that level. But we are concerned with, for example, the ability of doing distributed computing. For example, a master node that shares jobs to some computing nodes and then has to retrieve them and has to retrieve a certain value, a certain result, despite some nodes may be stragglers and respond late, right? So then you can use coding, and in fact very sophisticated approaches to code such that basically you can really see a trade-off, and sometimes you can even prove optimal trade-off between computation and communication. It's clear that in order to cope with stragglers, basically every node must compute a little more because you need to introduce some form of redundancy. And so you can see that there is a trade-off that, and sometimes you can even prove is optimal between these two problems. The problem of federated learning is analogous, or there is something called gradient coding, which is the sort of where the master node needs to retrieve the sum of these gradients, and but of course it doesn't need to retrieve every single element. In addition, in the presence of stragglers, with federated learning, there is also some constraint on privacy. So you want, for example, the master node to retrieve the sum of the gradients, but not the individual data, and you can formulate certain privacy constraint in terms of mutual information, such as the mutual information between these and these, given that is zero, which means that whatever the master node of an eavesdropper can do, if the mutual information is zero, it means that the privacy is perfectly achieved. It's not like a computation limited privacy. You may always say, oh, but if I have a quantum computer, the information theoretic privacy is nice because basically is robust for any form of computation. Even the best quantum computer would not break the information theoretic privacy. Let's say, to get to an answer to your question, I think that there is now a fairly developed theory of computation and communication, especially in this framework of network coding that apply to distributed computing and algorithms that are, let's say, related to machine learning. The most famous one is federated learning. So it's not directly related to the learning task. Yeah. So we don't care about what kind of data, what kind of cost functions, what loss function, what kind of networks. But it's the architecture of the data sharing that makes sure that one can run a learning algorithm over a network. Well, the data sharing architecture, in a certain sense, is almost already there, in the sense that networks are there. A data center can be seen as a network because you have all these machines and they're all interconnected in some way. So, and typically it's not like everybody is connected with everybody else. There are structures. There is a hierarchical structure, a tree structure. Who knows? The problems that are typically posed is for a given computing task and a given architecture, what can we do in terms of coding to achieve a certain optimal trade-off between, for example, computation and communication, or robustness to dropout nodes, robustness to stragglers, and sometimes even robustness to so-called Byzantine attacks, where you have nodes that may not respond in a faithful way, right? They try to inject some wrong information into the process. So A more general question would be, for a given task, what is the most appropriate network or data sharing or network architecture? I guess that this is more what people who design data centers do. And sometimes you can't really choose. Right? If you run, for example, a federated learning across mobile users, well, you have to cope with the network you have. Everybody has a lot of pictures and information in their phones, and maybe you want to run a learning algorithm that federated learning algorithm that uses user data on their device by preserving the privacy, and the network is what it is. You have to find them where they are.
Yeah, so maybe in the integrated communication and computing scenario, the design objective may change. Mm-hmm. We need to change it to computing a predefined function as accurate as possible.
Yeah, for example, a question that I think is these nodes have a piece of data, and then they compute a local function and send the result and things like this. But of course, this is somehow part of the problem definition, right? A more fundamental problem would be if, for a given computing task, also how you distribute the functions, yeah. Right? For example, a typical example is today a lot of algorithms like recognition of stuff, speech, they basically take the raw data, send it, yeah. And then all the inference is done in the network. But do you really need to send the pixels or the time samples of a speech, or you could do like a pre-processing on your device and, for example, send some latent space or something. Yeah. So this is, I think that people are actively looking into these things, but probably still quite at the infancy. Yeah. Also because, again, is also a problem of generality, right? If you need to have a few layers, a few pre-processing layers for every possible application on your phone, yeah. But there are countless applications, right? Then it will be very, very heavy for the phone to do this, right? On the other hand, probably, you have apps that now are just sampling raw data and sending, and maybe these apps will be then, say, augmented by putting a little bit more intelligence, a little bit more software, especially when devices will have, or maybe they already have, some high-end devices, some processors which are designed for AI, like tensor processors and things like this. Then you may imagine that these apps would run some layers, some pre-processing layers on board, and therefore send much more parsimonious information to the network.
Yes, so the integration of computing and communication is still on its early stage. Right?
Yeah, it's early stage. I think it's mainly driven by applications, but with the widespread use of AI as a tool, a toolbox in many different things, I think that it come very quickly, because it's clear that the phone cannot run a large language model, right? It's just too big. Right? But the pre-processing, the sort of front end that does a smart pre-processing before sending the data and runs on board with a specialized embedded processors that can do these things very efficiently, I think that this is almost already there, but is going to be more and more.
When these techniques are combined together, what new theoretical problems will bring?
That's a very good question. So, if we look back in history, there is a paper by Aaron Weiner of Bell Labs that I think is like
70s.
Something like this. It's a very old paper where he looked at the capacity of a cellular system and said, okay, why don't we consider the joint processing of all the base stations?
Yeah.
And it turns out, and so in that case, for a very simplified model, which is now referred to as the Wiener model,
Yeah.
the very simple model for intercell interference and regular topology, he could even write down some expressions in closed form. And so this idea of joint processing of all the base stations has been around for a long time. And then it has been periodically rediscovered and periodically also somehow judged not so interesting. So we have now there are this cycle. At the time of 4G, at some point, some people start calling these things like COMP, coordinated multi-point. People made experiments and concluded that actually COMP was not really helping. But why is that? Because they applied COMP, so they applied this joint processing, to a network that was designed in order to be cellular. And a network that is designed to be a cellular network is a network for which there are very, very, very few points in the network coverage that actually can benefit from the transmission from multi-point, because you want to guarantee coverage, and you have designed this network such that, given the sectors and the layout and the frequency reuse and all these things, essentially the network guarantees a good coverage without the need for multi-point transmission and coordination. Then other people came up with this idea of cell-free user-centric, right? So what is new about cell-free user-centric? I think that the main new idea is, first of all, the fact that even in COMP, the so-called coordination or clusters were infrastructure-centric. You would say, okay, you have these three sectors cooperate, these other three sectors cooperate. So these cooperation clusters were determined by the infrastructure, not by the user. The idea in user-centric, the idea is that there are many more small, let's say, infrastructure terminals called RUs, radio units. So instead of having these classical base stations, we have something more like a Wi-Fi access points, right? There is one every room in a building, or one every 20 meters in a campus, and so on. And then the cooperation cluster is user-centric, meaning that every user is served by a set of radio units in its surrounding, and this set depends on the user, is not predefined. Yeah. The first novelty is, I would say, at an architectural level, something that is not fully acknowledged even in current papers, but something that we have considered and studied quite in depth. You need to have a flexible front haul, because the data streams to and from a certain user go through a bunch of radio units and have to be then somehow collected or generated by some nodes in the network that typically, in the language of the so-called disaggregated architecture, are called decentralized units, which are essentially computing nodes, edge computers, that implement the physical layer, typically in software now. And it's clear that one must be able to convey this data through a flexible front haul. If you have a bunch of fixed connections, then you are infrastructure centric. You need this level of flexibility. I think that these, from a network architecture viewpoint, for people who study eCPRI and whatever transport protocols on the front haul, is challenging, as is different from a simple taking a base station and disaggregating it. Because take a base station, disaggregate, and you have like a computing node that communicate with like a fixed point-to-point links to say remote antennas, is not the same thing. You don't have this level of flexibility. Another aspect is the scalability. So it is unthinkable to convey all the signals in a single point. As the network increases in terms of area for a fixed density of users and radio units, the rate that it's required to be conveyed at a single point, a single centralized processor, explodes. So you need necessarily a decentralized processing, something. So there is a mathematical definition of scalable self-free networks, for which you say, for given fixed density of users, radio units, and decentralized units, as the network area grows to infinity, the rate at every link and every node and the computational burden at every computation node remains finite. This automatically means that the network cannot be just a multi-access or a broadcast. So it's not just a giant MIMO. It has to cope with interference. When you have these limitations, it means that some nodes generate signal that is unknown and cannot be handled by some other receivers, and this is an interference network. And the third, I would say, main novelty is that the nodes in the network have only a partial view of the network, and this is intrinsic because in a cell, you may say, okay, we have pilots, we do channel estimation, channel reciprocity, all the nodes so all the users in a sector receive a certain decent signal, they send their uplink pilots. So at the end, more or less, we are not very far from the situation where all the nodes know the channel. There is like a shared common information, which is a channel state. In a self-free user-centric network, because of this scalability, you necessarily have to reuse pilots across the network. And so if you have two users that share the same pilot, it's clear that, well, first of all, there is pilot contamination. So a node projecting on that pilot receives the superposition of a channel of this user and channel of that user. But somehow it's clear that if a pilot is assigned to, say, a certain user and is reused by another user, the nodes that are devoted to that user basically ignore the presence of this other user. This other user is, because it has the same pilot, it's unrecognizable. So in this way, the information that every node has on the network is partial. And this creates some little twists. It's not only a problem of, say, broadcast and multi-access interference, but it's also a problem of partial information, which makes things quite interesting. And there are recent works that have addressed these issues in a quite nice way. So I would say it is, of course, this self-free, massive MIMO, user-centric is another version of, say, multi-user MIMO in some sense, but has some distinctive features, both at the level or at the practical level of, for example, designing a flexible front haul where nodes can route information and in given ways, and also the theoretical level that make it a little bit different from whatever has already been done.
Yeah.
These are the main issue. Of course, there are many other practical issues, like, for example, the problem of synchronization, which is very important if you want to do multi-point transmission and joint precoding especially in the downlink, you must be ensure that these radio units are perfectly synchronous. So the frequency and even at the single sample, if you want to ensure reciprocity, they have to be synchronous at the sample level, which of course this can be very challenging, but this is something, for example, that people are addressing right now with the timing protocols running on the front haul and things like this.
Do you think these two big problems have already been solved or have almost been solved? And in the near future, are there any new big problems in the wireless communications?
That's a very, very fundamental question. Well, first of all, let me say this. Fading and interference, traditionally, in the old days, they have always been seen as foes, as enemies. So combat fading, combat diversity against fading, coding against fading. Same thing for interference, right? You want to try to eliminate interference as much as possible. All the traditional design of orthogonal access and carrier sense, Wi-Fi, collision detection is all about interference avoidance, right? More modernly, and in a certain sense also thanks to information theory and advancing communication theory, we have now embraced both fading and interference. For example, in MIMO, a rich fading channel is a resource. Is not something to combat, but in fact, the richer the channel, the more degrees of freedom you have, right? You have a full rank, nice matrix. And in addition, there is also this idea that, let's say, when you have a frequency selective sense, so when you have a large bandwidth, thanks to OFDM, essentially, we can now see these as parallel channels and therefore cope with the frequency selective fading quite well, embracing it. Interference, same thing. It turns out that especially exploiting the spatial dimension, so the antenna dimension, basically, we can, in fact, pre-code and transmit multiple users on the same time frequency slot. So this sort of avoidance in the time frequency domain is a little bit obsolete. Now with the MIMO and massive MIMO, we try to pump as many users as possible on the same time frequency resource. So this is just to say that the perception of these two aspects that you have mentioned has a little bit changed in the modern wireless communication. Well, first of all, let me say that there is still one bottleneck. Is still related to fading. Is about, let's say, the time variations. So right now, thanks to OFDM, we can cope with the frequency selectivity very well. Time selectivity, so rapidly varying channels, are still very bad guys. The mechanism to estimate the channels in order to be able to do this pre-coding require some delay, some piloting, and some periodicity in the channel sounding. And when the channel varies quickly, performance degrades. So I would say that, for example, there is of course, a now quite well-developed theory of signaling in alternative domains, the famous so-called Doppler delay domains, or TFS, and various things that somehow is more adapted to pumping the signal in the dimension where the channel is mostly invariant, which it turns out to be the Doppler delay domain, not really time and frequency. Of course, an interesting avenue, or maybe an interesting dimension to bring in in the standardization phase, it could be for some niche communication system with a particular needs, but why not, right? If these rapid time variations are a system bottleneck, one should be able to cope with that. Another aspect that I think has been somehow neglected and now is becoming very relevant is the aspect of complexity, in the following sense. Right now, so the way we cope with fading and interference is mostly multi-antennas, all digital processing.
Yeah.
But we also want a large bandwidth because we want a high data rates. And so now we have this really high complexity in the front end because we have hundreds of antenna ports. Each one has to sample a signal that maybe is 100 megahertz or 400 megahertz, right? The complexity of these things becomes enormous. I believe that there is, in fact, a valid direction, somehow rediscovering analog processing. Analog processing, especially in the RF domain. So today, with techniques based on metasurfaces and various say, antenna design that are unconventional, let's say, not the classical array with the all digital processing, it is possible to approach the same performances with all digital processing with significantly simpler hardware and above all a significant increase in energy efficiency. And the reason is the following. When we do our information theory calculation, we always plot spectral efficiency rate as a function of, say, signal to noise ratio. So when we talk about energy efficiency, well, we are already energy efficient in that sense, in the following sense, that if I care about if energies transmit energy over the air, we already have the limits. There is no special thing to do. The thing that we have to acknowledge is that the energy that a network actually consumes is not just the RF power that is put over the air by the devices. There is at the transmitter side, there is an enormous power expenditure just to put that RF power over the air. The efficiency is quite bad. There is a lot of power consumption in the power amplification that is simply just burned by the devices, the so-called DC power of a power amplifier. And at the receiver side, of course, there is a processing power. And the processing power can be significant, right? So if one can somehow bypass some of the processing using a clever analog processing, is probably an attractive direction that may allow eventually longer battery life or better energy bills for the operators which are burning a lot of money in running their network because the base station consume a lot of power. Right? Yeah, so I think that this is definitely something that has been a little bit neglected. So we have always somehow worked in the assumption that Moore's law is going to help us. But Moore's law help us in computation, and so far has been okay when we talk about digital computation. But when we look at, for example, the power that's burned by RF circuits is not so good. Moore's law doesn't apply. A to D conversion, Moore's law doesn't apply. And even now, the digital computing, we know that, from our AI friends, we know that energy consumption is one of the major system bottlenecks. So it's maybe something to take into account.
Yeah, I think you raised two very important points. So one is how to deal with the time variation, and another one is analog processing, especially the second issue may be neglected for many years. And this may play an important role in the future.
I personally I'm not a big believer of this so-called RIS, whatever, reconfigurable intelligence surfaces or reflective intelligence, or whatever they are called, as elements that you put in the environment and change the propagation environment. Honestly, I think that people haven't really thought through. But meta-surface technology as part of the antennas or part of the even part of the devices may actually be a game changer.
Yeah. What do you think about the impact of AI on the information theory research? And is AI likely to change the research paradigm for this field?
Okay, I think that there are many different answers here. Impact of AI on information theory, until AI models will not be able to discover new theorems in general, but this would be much more. There will be impact on AI on mathematics. Then I think that there is not a lot to do, in the sense that you can ask the best large language model to prove the capacity of the general broadcast channel, and I bet all my money that it will not be able to do it, to come up with an original proof that is correct and is actually not already known. Of course, when AI will be able to come up with the new theorems in mathematics, then maybe they will also be able to contribute to information theory, which is essentially a branch of applied mathematics to a particular domain, right? So at the moment, I don't think that we are there yet. I'm a little bit skeptical so people now use AI for everything. Every time there is a neural network, we say AI method. But after all, a deep neural network is a computing algorithm. The traditional way in which we have considered things, the so-called model-based, is I have a problem, I build a model, and then I come up with some clever idea to solve my problem for that model, right? And so you may say, okay, the Kalman filter, great. I have a problem, I model it as a Gauss-Markov process, and then I come up with the optimal estimator or the optimal one-step predictor that is recursive and is the Kalman filter. Great. Same thing for coding theory. I have a problem, I don't really know what to do, but eventually, more or less, I send bits and I get bits that are flipped or erased, and so I have this sort of super simple channel models that are very prototypical, but they are general enough such that we can build a theory of error-correcting codes. And then people struggle with algebra, with graphs, with polarization, belief propagation, etc., etc., etc. I would say I really don't like to call it AI because I don't think that it's intelligent. So the problem of artificial intelligence is that you are assuming that somehow there is some intelligence. It's algorithms like everything else, right? But somehow the approach of this, let's call it AI conventionally, even if I'm a bit skeptical about the term, is that is almost like reverting the picture. I have an algorithm architecture, which is neural network. Maybe I can choose the structure of the neural network, so convolutional, autoencoder, transformers, whatever. So this requires a little bit of intuition. And instead of somehow building a model out of logic, physics, approximation. I just somehow adapt my predefined structure to the problem through data. This is a little bit the idea. And this can work very well. I mean, we have seen in many applications, especially application where the modeling done with pen and paper is lacking. These approaches are extremely powerful. One for all, speech recognition, right? People have been working on speech recognition for ages. Like more than 30 years ago, when I was in France, a colleague of mine came from IBM, and his claim of fame were some speech recognition. And what did they use? Some sort of hidden Markov models. A hidden Markov model, the famous Baum-Welch algorithm, which is in coding we call it a BCJR algorithm, but essentially is a sequence estimator that spits out posterior probabilities. It was like this, right? And this stuff didn't work at all. I mean, all these answer machines, and it's like everybody's experience. You try to speak to these automated machines, and they don't understand anything. Now, suddenly, this problem, you speak to Alexa, you speak to whatever, and all these digital assistants, they work like a charm, right? Because the models of speech were very simplistic. For that simplistic model, the Baum-Welch algorithm is optimal, but the model was simplistic. Yeah. Now, whatever network they use is much better, because essentially it's a data-driven approach. It doesn't explicitly build a model and somehow learn from the data itself, and they somehow the structure, the algorithm is expressive enough to somehow adapt and learn and be trained such that the performances are amazing. And so for translation, for medical image recognition, like cancer detection from medical MRIs or whatever they do, there is a set of problems where the models are lacking, or it's simply difficult to come up with models that are tractable, where these approaches are real impact. There are problems where the models are actually very good, and then I'm very skeptical. Like if my problem is to design codes for the Gaussian channel, and actually when you do the measurements and you have a transmitter and a receiver, and you look at on the spectrum analyzer or your scattering diagram, you really see the modulation point with some Gaussian noise, because the synchronization is good, the phase and frequency is all okay, and therefore the problem is really y equal to x plus z, and z is Gaussian. I'm sorry, we know exactly what to do. Yes. There is no magic. Maybe a neural network can discover some strange constellation of points, but this will never really beat in the range of parameters that we are interested in. So block length above 100 symbols, and essentially I think we are pretty good. So I would say sometimes people have used these things to essentially as a tool to write papers. I don't necessarily like that, because the results are very difficult to reproduce. It's very difficult to make comparison. It's never really sure what people have done. You download the stuff on GitHub and it doesn't run. So it's so much nicer to have some nice algebras and nice algorithms that you can redo yourself, test. However, there are of course problems that require where the modeling is lacking. Like for example, in a simple, so you mentioned compression of text, which of course the algorithms that are used as state of the art for test compression are a partial pattern matching and context reweighting and all these things. Of course, use models that are not exactly correct, because human language is a complicated thing. It's not necessarily a tree structure. So this probabilistic is what we use to describe it, right? But it's not like that. And when you go to like image compression or video compression, it's even more true. It's harder to do, by the way, also for the AI methods. But the reason why every new generation of image compression or video compression we get better results is that nobody knows where the rate distortion function is. Because we make models that, what is the statistics of like a video? So these methods are very empirical. Who tells you that this Wavelet transform is better than this other Wavelet transform? It's just a way that people have found to somehow, that makes sense, but it's very empirical. So a machine, a network that somehow learn from a lot of data for sure has a better chance to improve if it is well designed and well trained. So in this sense, I would say that to wrap up, I would say that these techniques are very effective, especially and make sense in those cases where our modeling is lacking.
Yeah.
So either the models are too complicated to be tractable, or we make artificially simplified model for tractability that do not really represent faithfully the reality. In the cases, more classical cases where the models are faithful with respect to reality, and we have techniques with some optimality, something that you can prove, and then using learning approaches is a little bit like a little bit of an exercise, but I don't see the real impact there.
Yeah, so it depends on whether we have an accurate model.
Yeah. Right. And if these models are tractable. Sometimes you have a very nice model, but it's just too complicated to handle. And so even a model-based approach would be simply, you don't know what to do.
Yeah, sure.
Then you resort to a learning-based approach.
Yeah, I'm often curious about it because, as you have mentioned, there are so many clumping research directions, for example, in our field. Mm-hmm. And sometimes we always trying to balance our time by investing, like what you mentioned, low-hanging fruit, and also something you are really interested in.
Right.
And especially under the current climate, I would say that people are driven for citations and the impact. However, if you are really want to tackle on a very difficult problem, it's really hard to have good citations, especially when you are at a young age. But you need these citations for a career and a starting point. Yeah. So, any suggestions for this?
I think it's at the end of the day, it's a matter of luck. Then, in order to somehow make it, the intuition of identifying good problems to work on is very important. Maybe just by so-called serendipity, right? by accident. Okay. You know why I worked on BICM, and which was the beginning of my career. Essentially, it's still my most cited paper. Okay. This was because at the time when I was at the Polytechnic of Turin, the topic that everybody were working on, and during my PhD, what I did and others in the same office with our professors at the time, so Bilieri and Benedetto, already still well-known names, right? Was coded modulation. Everybody were working on coded modulation. Everybody crazy about coded modulation. Angerboard codes, trellis coded modulation, with beautiful theories, codes over groups. And I had really, this coded modulation was like, I had enough. I really had enough. And then my point was, let's try to do something that is like completely against coded modulation. This idea of random interleaving was already there because the turbo codes came up in 93.
Yes.
And I was very lucky because Bilieri had knew about the turbo codes because he had friends at Telecom Paris. And so we had the preprint of the thesis and the paper on turbo codes before they were presented. And actually I implemented this stuff because he told me, oh, you have to look at this. They must do some error. There must be some error here. And so I and another guy in Turin, we implemented this, we simulated the turbo codes. And before they were presented in ICC 93 in Geneva, we knew it was correct. And I remember there were people, when Beru presented his stuff, and there were people saying, oh, this cannot be, come on. And I was just a little student there, so I shut up. Right? I didn't say anything. But I knew it was correct because we independently reproduced their results. So this idea of randomizing and using interleaving was there somewhere. So I think that putting together a little bit of information theory, randomization of interleaving, so the BICMK, and the idea that, okay, now we have been working for like 10 years on coded modulation, and suddenly now there are these binary codes, which are like never seen before, and they're incredibly powerful. What do we do with, you know? So the idea was essentially and this came up like this, right? Like a complete serendipity. I think it's a matter of luck. It's just to bump into a right problem that it turns out to be also pretty simple, and that you can actually do a paper that people understand. I personally think that being too influenced by trends is not good. First of all, unless you are the trendsetter, so if you are the one who initiates something, you're always late. Now, if you jump on a large language model after OpenAI and DeepSeek, sorry, you're late. So often is better to, my feeling is always, is better to follow your interests and look at what you are interested in